Hello and welcome to this InfoBlocks DNS and DHCP Fundamentals webinar. My name is Reggie Ledesma and I'll be your presenter. This is Module 2 addressing DNS name resolution, master and slave servers, timers and transfers. An auto run of this presentation takes about 20 minutes. Let's quickly review the table of contents page before we begin. This slide is your table of contents. During the presentation, you can click on the TOC link to return here at any time. Each bullet item above is a link to the topic, allowing you to navigate the presentation as you see fit. Some pages contain drill down links that provide you with extra information. Clicking back will return you to where you left off. If you allow the presentation to auto run, you will see each of the topics in the order shown. The first topics to be addressed will be an overview in nature. We will cover the DNS messages, name resolution, name server functions, timers, and zone transfers. In the next couple of slides, we're going to take apart a basic DNS query to learn more about the protocol in general. This will help us understand what DNS can and cannot do. In a previous presentation, we've seen how the most common query is a request for the address of a given name. When we looked at the DNS record types, we also saw how one type of response we might get is an indication that the name we have is really an alias or an alternate for some other canonical name. There are other valid queries a client might ask of DNS. Some are shown, but we want to make the point about what DNS cannot tell you. A name server will answer a question based on the information contained in the query, domain name, class, and type. It will not provide answers to questions not found in the query. The basic DNS message query and response look very similar. Both have a common header, Q&A sections, authority, and additional information. This animation shows how the original query from the client has a null entry for the answer. The response from DNS is the same message but with the answer area filled in. The header of each message describes much more about the message than we have time to dig into here. Click on the header link to learn more about how the header describes the message, whether it's a query or response, whether the message is authoritative or not, or other attributes like whether recursive processing of the query is desired or available. In terms of TCP/IP, DNS uses UDP port 53 in most of its communications. If that fails, it can use TCP through the same port. TCP is used mainly for zone transfers. Rather than force every application to understand the format of a DNS message, DNS implementers provide a functional resolver. On some operating systems, like Windows 2000, the resolver is actually a system service as shown in the slide. The resolver is usually a set of library routines that applications can use to translate high-level requests for data in the namespace, in other words, the address for a given name, into the appropriate DNS query message. The routines also handle transmission of the query message, any retransmission, and interpretation of any response in the message. If you need an alternate way to view your settings, you can use ipconfig with the /all parameter. The process by which resolvers and name servers operate to find data in the namespace is called resolution. The name server that receives the query begins resolution by finding the best name servers and querying them. The best name servers are those authoritative for the zone containing the answer. The next best name servers are those authoritative for the zone's parent because they're only one referral away from the name server with the answer. In the worst possible case, the name server begins by querying one of the name servers authoritative for the root zone. In the example on this slide, a name server asks DNS for the address of north.a.com. All possible name servers know how to find the root server because of a preloaded hints file included with every build of bind. Coming back from the root server is a list of name servers for COM. So, the first level domain servers get the query resolution task to the second level servers. On the previous slide, we found the address for COM. On this slide, we illustrate the use of previous results to query for and locate a.com. The second level gets us to the third level and so on until we have the name server we want. When multiple records must be returned, DNS rotates through them in round-robin fashion. When the original name server does get the answer, it caches it to speed up repeats of the same search. Queries come in two flavors, recursive and iterative. Recursive queries place most of the burden of resolution on a single name server. Recursion means that the name server will repeat the same process, asking a remote name server the same question until it receives the answer it needs. Iterative queries, or iteration, means that the queried name server gives the best answer it already knows back to the querier. No additional querying is required. The queried name server consults its local database looking for the data requested. If it doesn't find the answer there, it finds the names and addresses of the name servers closest to the domain name of the query in its local data and returns that as a referral to help the querier continue the resolution process. Note that the referral will include all the name servers listed in the local data. It's up to the querier to choose which one to query next. In this slide, we demonstrate how a server will respond with an answer if it has one. The answer does not have to be authoritative for the requested domain. The query goes out to the name server and an answer comes back, but the header indicates that in this case the answer is not authoritative because the name server either found the answer in its cache or asked another name server. In the second example, the header AA field equals 1 means that the answer is authoritative for AA.com. There are two types of DNS name servers, primary masters and secondary or slave masters. In this context, secondary and slave are synonymous. While both master and slave servers are authoritative for a zone, the two differ in where they get their zone data. A primary master gets its data from its own stored files. A secondary or slave gets its information from another DNS server which is also authoritative for the zone. From the client's perspective, primary and secondary make no difference to its query. Both are authoritative for the zone. We've seen how a primary master gets its zone information from its own storage, and how slave servers get their zone information from a primary master. Next, you need to note that a given name server can act both in primary and secondary roles for different zones. In this diagram, we can configure the right-hand server to be a primary for a different zone. In designing or learning about your own DNS topology, note that a single DNS name server can be a primary master for one zone, A.com in this diagram, and a slave master for another zone, B.com in this diagram. Also note that slave servers that can themselves be masters to other slaves. In this example, look at the left-hand server where it's a slave for B.com. This server can itself be a master for other slaves. In this case, we would not call it a primary because it's not getting its zone data from its own storage. Master, slave, primary, secondary, they're all internal names for how servers get zone information. To the outside world, there are no such things as a primary, a secondary, a slave, or a master. All are authoritative name servers. DNS involves a lot of name lookups, which suggests that the system overall should be slow due to query volume. In practice, you know that it isn't slow at all, and caching is one reason why. Local name servers are constantly saving the results of queries so that they can reuse the results as often as needed. But caching requires limits, because while some zones rarely change, others change frequently, and thus cached results that describe the zone must be updated as well. This slide describes some of the timers used to maintain the currency of a name server zone cache. First, from the A record, we find a TTL or time to live value expressed in seconds. This timer tells any other caching server that this zone changes fairly often because 86,400 seconds is equal to only 1 day. Any server caching the results that include this record will know that this zone data is good for 1 day and then will need to be refreshed. The SOA record tells the caching server more about the currency of the data for this zone. First, it has refresh times, which is very similar to an A record TTL timer. This value tells the slave server how often to refresh the zone data for this zone. Then, if the primary server for the zone doesn't respond, how long to wait before retrying, and when to expire and delete the zone data if the primary server never responds. A negative caching TTL tells a name server how long to keep an answer that came back with a negative response. From the slave's perspective, then, the relationship runs as follows. When the refresh timer expires, compare the serial number with that on the master. If the serial numbers are equal, restart the timer and exit. If the serial number on the master is incremented, the slave knows it needs new zone data. Request a transfer, NAXFR, from the master. If the master doesn't reply, retry in 7,200 seconds. If the master doesn't reply in 2,592,000 seconds, delete the local copy of the zone data as it is now too old to use. The slave cannot now serve information about this zone. The TTL value held by a name server is constantly decremented as time passes, so clients are given true time remaining values when they ask for the remaining TTL. When the TTL goes to 0, the name server drops its cache of zone information. In this animation, we see how a name server receives a request for zone information from the first client. It then receives and caches a 24-hour copy from the authoritative master for the zone. Then later, after some time has passed, other clients request the same information from the same name server. The name server doesn't need to go back to the master because the TTL is still valid for 14 hours. A third client, still later, finds the zone data still valid but only for 2 hours. In this way, the name server doesn't artificially extend the zone's TTL and thus circumvent the intentions of the network administrator. As mentioned earlier, caching can help performance in 2 ways. The best known way is to keep the results of successful queries. Lesser known and understood is how caching works with unsuccessful queries. This slide and animation illustrates how a query asks for information about xyzzy.dns.pn, a non-existent name. The authoritative server for DNS.pn knows the requested name doesn't exist because, as the authority for DNS.pn, this server would know about it if it did exist. Looking at the header, for the reply we see the name error code NXDomain. The answer code 0 tells us that there is no RR data in the answer section. The authority code is set to 1. That tells us that one named server, who is authoritative, told us that the name does not exist. Name servers have some additional logic that speeds things up. This diagram demonstrates how a server tries to pick the fastest of the root nodes to answer its queries. First is the query, followed by a list of matches, which for the root nodes, recall, are 13. The name server now has a list of 13 possibilities for its next query. The name server follows some simple logic to pick which one to use next. Each name server maintains a list of RTT or round-trip times for different servers. Each time it has a choice between multiple servers, it chooses the fastest one. Using this server, it times the response for this new query and updates the record. By doing this, the RTT tends to reflect the overall load on the DNS topology as a whole. When one server that used to be the fastest begins to slow down, its RTT will be updated and a new, faster server may be queried. But what happens when a server set is first queried and no RTT data exists? In this case, a RTT table for a data is initialized with low random numbers that actual usage will update and correct on the fly. After this random initialization, the RTT data is used just as if it was based on actual times. Why does the new sample constitute only 30% of the new RTT rather than the whole thing? The short answer is that bind uses a highly weighted algorithm for keeping an average RTT. The server is saying this response may be extra fast or extra slow outside the average, but since it's the most recent, I'll give it the most importance. So it receives 30% of the weighting, and the prior 7 times received 10% each to make 100% running total. Why is a name server's initial RTT random? Because it does not know any real values. All it can do is assign random values. These values do not even constitute guesses. Why low? Lower than what? By knowing that these values are randomly assigned, still wants to have valid RTT tables up as soon as possible, so it does not want to start with artificially high numbers that may take longer to normalize than lower values. Why decay the RTTs of name servers not chosen? You have to consider why a server was not chosen. The most obvious answer is that it's slower because of its geographic region relative to the querying name server, but it may not have been chosen if the RTT was high, maybe even off the chart because it was offline or connectivity was suffered. In this case, it would have an RTT that would be astronomical, and as such, it would be impossible for it ever to become part of the working group of name servers for that domain, even if that name server were right across the street. So bind in its infinite wisdom decrements the RTT of these name servers so that eventually they become part of the working group again. Actually, bind also has logic in it that says, I've got a server that looks like it's down, and I'm going to query him every X times just to see if he or she is back up again. They don't hit that server often, but they will hit it regularly. The traditional way that a slave server maintained its zone data was to check the SOA record with every refresh and request an AXFR, asynchronous transfer, if the serial number revealed that the master had changed. The new and improved method is called DNS notify. Where implemented, the master maintains a notification list of servers to be notified upon each zone data change. This improvement decreases Increases the amount of time a slave uses outdated zone information regardless of the SOA record refresh setting. A second improvement is called an IXFR, or incremental transfer update. With IXFR, only the changed portion of the zone data will be sent to the slave name server. This can save lots of packet traffic if many slaves were involved and/or frequent zone updates are used. A lot can be learned about a query if we examine the message header used. The first field highlighted is the opcode. This indicates whether the message as a whole is a question query or an answer response. The RD field indicates a request for recursion. The status field indicates whether there was an error or not. And finally, the answer field describes the answer that will be in the latter portion of the packet. The answer to a typical query might look like this. Note that the header tells us that this was a query, that there was no error, and the ID of the original query was 29400. We can also see various flags set, including the AA, or Answer is Authoritative flag, and other information about the reply. This completes this DNS DHCP Fundamentals webinar. We thank you for taking the time and invite you to review all the other webinars in this series.